Thanks, Arya. It's, it's been a great workshop. I'll try not to spoil it. And so this talk is based on joint works with Jonathan Kellner, Freddie Coiler, and Dhruv Rohatgi. And the slides are mostly due to Freddie and Dhruv, which they kindly allowed me to borrow. So the basic setup is I'll start with the bread and butter of ML, which is supervised learning. So the algorithmic problem that we're tackling is you're given as input some training data. So IID pairs, xi, yi, at least no noise or anything like that, from some distribution. And our goal is to find a function f that can predict the label. Okay, we are not trying to do parameter recovery. We're not trying to do proper learning. All we care about is prediction error. Okay, find me some function f, which on a new sample like 0 and y0, has small error in prediction measured in squared loss here. Okay, so it's basically like you have some ground truth, have some training points, and then I fit a degree phi curve, I get some error from that. Okay, and in many applications, one of these you see this sort of dichotomy where you're trying to minimize sample complexity. So for some applications, you don't care if I'm slightly off in the optimal sample complexity, and in some, you actually do care about getting close to the optimal sample complexity. And for many of such questions, we have seen that there are computational obstructions to achieving this statistical optimality. And this is from a picture of a program that was on Simon's, trying to kind of find these different landscapes of where you have these sort of obstructions, where you cannot get optimal sample complexity with efficient algorithms. Okay? And today I'll talk about such a scenario where for the problem of sparse linear regression. And here when I say optimal, always think for sample complexity. I'm willing to lose a lot in runtime, but not be inefficient. So it's okay to be quadratic, cubic, whatever. I'm not aiming for optimal runtime, but optimal sample complexity and efficient runtime. Okay? And sparse linear regression, of course, is a very fundamental primitive with lots of applications. You might have heard of compressed sensing. That's a special case of sparse linear regression. And it also shows up in causal models, graphical models, many, many places. Okay? It's interesting by itself, but also appears as a subroutine in many other learning algorithms. Okay? So what do we know about it, and what do we don't know? So one thing that will be maybe somewhat, or at least it was somewhat of a surprise for us, is that when we first started working is even when all of this will become more clear, covariates of the random variables, covariates of the distribution, the inputs, have small correlations among them. The algorithms that are most often used, like Lasso, basis pursuit, and all of these other sort of variants, they fail in achieving good sample complexity. And it's not just that our analysis fails for them, they actually fail in practice. Okay? But in many interesting cases, you can find tricks to fix them. Right? So find some nice algorithmic ideas which are pretty efficient, which will make the old algorithms work. Okay? So that should be the main takeaway. So let me now talk about the setup of the problem, and we'll focus on Gaussian sparse linear regression, which I think is maybe one of the easier cases of sparse linear regression, as long as I don't allow for condition number bounds, which will become clear. Okay? So what is Gaussian sparse linear regression? So we're getting samples, xi, yi, as before. We are in an unsupervised learning setup, but the x's are coming from some multivariate Gaussian distribution. Okay? But it's not like standard Gaussian. They have some covariance which is being used to generate that. N0 sigma, we'll call these xi's covariates. Right? And each xi here is an n-dimensional vector. Okay? I denotes the sample. And yi is the response, which is obtained by taking a sparse signal w star times the covariate xi. Okay? And typically, we also add some noise, where the noise is assumed to be independent and Gaussian for now. It can also work in more general scenarios. But in fact, for this talk, as we'll see, I'll focus on the noiseless case anyway. Okay? So this is almost like a linear regression problem, but we have this additional assumption that W star is k-sparse. Okay? And our goal is to predict yi for new samples. And for the rest of the talk, I'm only going to focus on the noiseless case, sigma equals 0. Our upper bounds work for more general noises, and the lower bounds hold for the noiseless case, so it's kind of going in the right order. But everything becomes simpler and easier to understand when there's no noise. Okay? And you can also think of it in some kind of matrix notation. You might like it better. So I can form a matrix where the rows of the matrix are the samples, like the covariates X, right? Then what I want is to solve this linear system, y equals x times w star. Okay? But it's not that I want any solution for it. I want a solution where w star is sparse, or do something else, but it has to generalize better. Okay? Any questions about the setup? Okay. So what do we know about this problem? The first thing, which is kind of very nice, is that information theoretically, you can do something very strong. No matter what the covariance matrix sigma is, if I just tell you that w star has only k non-zero entries, k log n samples suffice to get small prediction error. Okay? You cannot recover the w star in all cases. For example, sigma might have like ill-conditioned things. Maybe a variable appears twice. Then there's no unique explanation. But for what you care about in terms of prediction, you can always do it with only k log n examples.
Okay. Is there a dependence on the prediction error?
Right. So you can actually recover it with k log n. So prediction error, if you have I'm considering the noiseless case. So that's why it's k log n. Otherwise, it's k log n over sigma squared. Okay?
You're saying that's the identifiability, like you can just get the vector period.
Exactly, right? In the upper bounds, you'll basically say even getting small prediction error is hard. But as I said, everything goes through even when you have noise. It's just easier to think about because it's going in the right direction. Okay? So, but on the other hand, that's like optimal sample complexity, right? K log n is great because it doesn't, if you think of k as being very small, like 10, 100, then only logarithmic samples are needed, okay? How about efficiently doing it? So the current state of knowledge is there is no algorithm which can handle it with little o of n samples, okay? And n to the little o of k runtime. I can always solve it in n to the k runtime by basically enumerating over all possible k non-zero coordinates, right? I enumerate all possible sparse subsets. That gives me n to the k runtime. And for that, each one I just do k log n. Okay? In fact, that's one way to prove the information theoretic upper bound. Okay? But if I allow you to say, okay, you cannot do this brute force enumeration, n to the little o of k, suddenly the only thing you can do is basically solve least squares regression, which requires n samples. Okay, you're completely ignoring sparsity now. So there's nothing in between that we know, even when the covariates are Gaussian. Okay? So the main challenge, I would say, in this context of sparse linear regression is what is the computational limit? So where does it stand? What can we do efficiently? And I should say that, as I said earlier, when sigma is even nicer, when the distribution on X is even nicer, we're already assuming it's nice because it's Gaussian. But now we're saying the covariance matrix is very well conditioned, like if it's identity. If it's identity, it's like compressed sensing. If it's well conditioned, you can also still do some stuff. Okay? So in these cases where sigma is well conditioned, there are various ways to define well conditionedness. For example, one way is to say, okay, the largest eigenvalue to the smallest eigenvalue of sigma is bounded by at most t. Okay? Then there are the standard, very widely used algorithms with their own, R packages and so on, which are deployed in many places in applied sciences, like Lasso, basis pursuit, dancing selector, orthogonal matching pursuit, and so on, which solve this problem pretty well. In particular, they get something like t times k log n samples, where t is a condition number.
So, Raghu, a question, maybe it's obvious, but so when you have a not well-conditioned covariance matrix, so in that case, it is very obvious to see that if you take n measurements or n samples, they're linearly independent, because you said with order of n sample, you can always...
Right, you can prove that it happens with high enough probability.
Okay.
Yeah.
You can just for analysis, just transform the space and make it identity. Just
Yeah, that's
I
also.
see, I see. Okay, yeah.
Or
So,
actually
sorry,
even
that's
just,
why it was stupid. But anyway,
or
I
even,
get it.
in fact, when you have n samples, it works for arbitrary distribution. It doesn't have to be Gaussian.
For sure.
Like linear regression generalizes O of n no matter what.
Right.
So that's even stronger. Like you don't even need the Gaussianity then, right?
So is there a way, like in compressed sensing, like in the full noiseless case, and if you have exact case sparsity in compressed sensing, since you can choose the covariates, you can do it with order of k, right?
Right,
Like,
right,
or you
right,
don't even
exactly.
need.
So, I mean, as I said, all of the stuff that we're doing works also with noise.
Okay, so that's
The
why.
upper bounds work with noise, the lower bounds hold even without noise. Okay? And yeah, so in fact, the upper bounds extend to the noisy setting just because we're reducing to these algorithms, and these are known to be pretty good. Right? When sigma is well conditioned, we can solve the problem very well. Like we can solve it in the agnostic, non-realizable setup. Okay, so we're kind of going to reduce the well conditioned case by doing some things. Okay? All right. So this is a state, this is a huge gap, and okay, you might look at, okay, what do we know in terms of barriers? Okay, the two things that we know are for sort of non-average case setup. Okay, this goes to what Arya was asking. If you're allowed to choose the xi's, you can do some strong guarantees. In the same way, you can, if you're allowed to choose the xi's, then you can also construct hard instances. Okay? But for us, we are in an average case setup. We have an underlying distribution on the data, and the distribution also somewhat nice. It's a Gaussian distribution, but the covariance is unknown, or covariance can be arbitrary. Okay? So if I'm allowed to fix this matrix X, then you can easily encode NP hard instances into it, and you get hardness results. And there are also lower bounds saying, okay, Lasso will itself fail if I allow arbitrary sigma. Okay, this is known. Okay, but we'll see that even these hard instances, which are known to make Lasso fail, can be fixed by some change of basis, by some simple changes of basis. Okay, we'll talk about that more. In fact, we'll see both versions of it, how we can use a change of basis cleverly, and what are the limitations of that. All right. So to summarize, there's this exponential gap for sparse linear regression in the Gaussian setting, where k log n is the information theoretic limit. Anything little of n, we are kind of hitting the brute force limit for efficient algorithms. Okay? So the two main questions then are, we are not able to solve the arbitrary sigma cases, right? So can we find at least interesting cases, like going beyond worst case over sigma, where we can get efficient algorithms? Okay? And if sigma is well conditioned, of course we know how to do, but that is very limiting, as we will see, even for some simple examples. Like if I just have one coordinate repeated, that violates well conditionedness. You might think, okay, this is a silly thing, maybe you can fix, but we'll see that even those actually make many algorithms fail. Okay? And the other question is, can you prove that maybe this problem is hard? Such a gap is necessary. Are there algorithms that we know cannot solve it approaching this limit? And here we cannot use worst case hardness guarantees. Like we cannot base it on NP hardness because our underlying distribution, we have a distribution. We are getting samples. Okay, we need some kind of average case hardness. So in this talk, I'll focus on kind of summarizing, or it's a mix of 4 papers where I'll first talk about how we can solve or get good algorithmic guarantees under some structural assumption on sigma. And this is going to introduce a tool that we call preconditioning. And then we'll see the limitations of this approach as well. Like it fixes a lot of interesting cases, but then it also has its limitations. And then I'll introduce another technique where you can handle other interesting classes of sigma and then show a lower bound for that as well. Okay? All right. So let me start with what it means to say, okay, I'm going to use preconditioning to solve this low tree width instances. To motivate this low tree width instance, I'm going to actually focus on an example, and then we'll just generalize it to the full setup. Okay. What's the example? The example is the random walk covariance matrix. Okay. So here the xi's are basically, okay, so they're written as Ri because for random walk. So my covariates are generated as follows. Ri is Ri minus 1 plus an independent IID Gaussian, IID N01 Gaussian, okay? So I have Z1 through Zn, which are IID N01, but my covariates are actually R1, R2 up to Rn, which are the prefix sums. So what is the covariance matrix I'm sampling from? It looks something like this, right? So the covariance of R1, R1 is like 1, R2, R2 is 2, and then it has this nice structure here, okay? So this is appears in many setups, like especially in time series data. If your x's are coming from time series data, often they have such structures, okay? And this is very badly conditioned, actually. Okay? If you think of the largest to the smallest, it grows with n, the number of variables, right? And as a result, none of the existing algorithmic guarantees apply, even when x is coming from time series data like this. It's a toy version of time series data, but even then we cannot apply the existing guarantees for Lasso and so on. And in fact, when you implement them, they fail very badly, right? So let's say I'm trying to do sparse linear regression, where x's are coming from this time, like xi minus 1 plus zi. And I run Lasso or basis pursuit, which is kind of one version of it. Then the number of samples you need to get small error is like much higher, okay, than what you would need if you had standard covariance. And we are going to introduce a new algorithm, preconditioned BP, which you'll see, where it does much better. Okay? And this is with sparsity 2. Okay, so n is reasonably big, but sparsity 2, you're saying that Lasso needs 402 samples. Okay, even for the small sort of just random walk example.
So Raghu,
yeah.
So your bounds did not distinguish between the case when the covariance matrix is known versus unknown. Does that make a difference?
Right. So for one of these, for this preconditioning based thing, we need to know the covariance matrix in the sense that at least we need to know the graphical structure. Because we don't need to know the actual values, we need to know the graphical structure. For the second part, you don't need to know the covariance matrix. Okay? But actually, that's a good point. For the information theoretic exponential gap, we don't know how to close this gap, even if I tell you sigma. I give you sigma, what can you do? We don't know. Okay? So we'll see that we can solve this sparse linear regression on random walk with almost like optimal sample complexity by preconditioning. And this will generalize, then we'll generalize it to kind of a richer class of sigma. Okay? So what is preconditioning? So preconditioning, of course, is kind of, if you're done in numerical linear algebra or sort of least square system solving, then it's a very important technical tool that people use. You might have an ill-conditioned system where gradient descent is not converging well. What you do, you precondition, apply some inverse transformation and then work in this space so that you have good convergence rate. Okay? So here we're kind of doing some kind of linear regression, but we're trying to do preconditioning, not to save on convergence steps or runtime, but on sample complexity. Okay? So formally, if you Lasso, which is kind of one of the main algorithms that people use for this, solves the following problem. I'm trying to solve xw equals y. Remember that's our linear system. But we don't want any solution to it. We want a sparse solution to it, right? Instead of looking for a sparse solution, usually I try to minimize the L1 norm of the vector w subject to satisfying this equation. Okay. If you had noise, I would just replace this with some kind of less than or equal to something or put a penalty and everything will work. Okay? So preconditioning just means that don't measure like sparsity or the L1 norm in the original basis, but measure it after doing a basis change. Okay. So S transpose W. So if S is invertible, right, then it amounts to first doing a basis change and then doing sort of standard algorithms. But it doesn't have to be invertible. It can be rectangular. It can be, you can use more features if you want to. Okay, you can do anything you want.
So did you know the covariance matrix when you were given, like do you know that distribution?
So we need to know the graphical structure of sigma. Okay, I'll tell you what that means.
Yeah, I see.
Okay.
Just clarification. So when you do the rotation, that will destroy the sparsity if you have in the origin.
Right. So that's why you cannot use any, I can obviously make sigma to the minus half, right, which would be great because now I have identity covariance, but then that destroys the sparsity, right? So you need to find a trade-off where maybe there's a preconditioning which doesn't hurt my condition number too much, but still keeps, basically you want some kind of bi-criteria thing. Okay, and we'll see we can do that for some cases. Okay, so let's go back to the random walk example. So here we have Ri is Ri minus 1 plus Zi, just a reminder. And our goal now is to do a basis change. Right? I want to work in a different basis. I want to replace this Ri's with some other linear combination so that the new variables are better conditioned, but I still want to preserve some kind of sparsity. Okay? So the first attempt might be I'm just going to try to subtract the variables. Right? So each Ri is Ri minus 1 plus Zi. Right? You have an independent Gaussian that's coming in every step. What if I do this basis change? Then these difference variables are actually independent Gaussians, so extremely well conditioned. So these W's now have covariance identity. Very good. But what's bad? The sparsity has gone to it's become very bad. The good is the WIs are IID, covariance is identity. The ugly part is that we lost sparsity. In particular, just to give an example, let's say I have one sparse signal in the original basis. Y was just R1000. Okay, I'm just picking one variable out. In the new basis, when I try to write Y, it says the sum of everything until then. Okay, the sparsity has gone to 1000. Okay, so I cannot use existing guarantees now. Right? So that's why this fails. So the challenge, of course, is you need to find a way to do this basis change so that each of these original variables is a sparse combination of this Wi so that you preserve the overall sparsity. Okay? And so this is our goal now. We want to preserve the sparsity.
So here, if you bucket things, would it work?
Almost, but you have to be a little bit maybe it's kind of bucketing, but binary tree bucketing. Okay? So the key insight that we're going to use is that many times, especially in this random walk example, you have this Markovian property, right? Which is, if I give you the middle variable, like let's say RT over 2, then all of the variables before it are independent of all of the things after it, right? So we're going to use this Markov property, the fact that you have this independence. And for Gaussians, when you have independence, let's say you do the conditioning out properly, that means that the covariance of the two is 0, basically. Right? As long as I have independence, when I scale it, I will get a good condition number. Okay? So in general, you have this Markov property that once I condition on Ri, everything after it is independent of everything before it. Okay, so how do we use it? Oops. So so let's say I write down everything in a binary tree. So x1, x2, x3, x4, x5, x6, x7. So the middle point is x4. So I want to say that, okay, if I condition on x4, everything before is independent of everything after. So what does conditioning mean? It's like a basis change in the context of Gaussians. So I replace every one of these variables with by kind of subtracting out how much correlation they have with x4. So I'm orthogonalizing. I'm saying that, okay, in my new basis, x4 is going to be an element. Right? I'm starting by adding x4 as a basis element. But then, it has correlations with the other steps. I need to orthogonalize, almost like Gram-Schmidt's orthogonalization. Okay? So I do that. So I remove x4 from everything. But then, I do it sort of recursively. Okay? So I first orthogonalize with respect to x4. Then in the left half, I go to the middle point again, which is x2, right? And then go to the middle point again and so on. So you have this binary tree, and you keep orthogonalizing with respect to things on the paths, right? So in this toy case, you can actually work through this without too much difficulty. I don't want to write the arithmetic because a little bit, it clears out in the end, but if I want to do it step by step, it gets a little messy. But the idea is you always orthogonalize or perform this sort of Gram-Schmidt style orthonormalization with respect to midpoint of the interval that you're working. Okay, one at a time. You do this log n times. So for example, here if you do this, you get this new basis, x1 minus half x2. It sort of looks very weird, right? But if you do the arithmetic and you check it, you'll see that all of these are exactly orthogonal to each other. Okay? So these variables, if I call these my new variables, their condition number is going to be 1 or very small. And what's the advantage? Each of the xi's is also a sparse combination of the new variables. Okay? So if I want to generate x4, or let's say I want to generate x1 from these new variables, how do I do it? I can write it as a combination of these things, of the new variables that I introduced. And the blow up in sparsity is only the depth of the tree. Like if I want to get to x1, which was there, I need to add up things on the path to it. There's a combination of the things on the path which gets you exactly that. And again, as I said, if you want to do the arithmetic, there's a direct way to do it. But doing it in this tree recursive way kind of generalizes better. Okay, you just always maintain this invariant that I can express what I'm generating newly from the old ones only along the path. Okay? So every new variable, every old variable is only a sum of log n new variables. Okay, so I got good condition number, and I kind of blew up the sparsity by k log n. Originally I had k sparse signal, now I have k log n. Okay? And now I can apply the old stuff. If you're a signal processing person, they'll say that, okay, what you did here is they went to the discrete Haar wavelet basis. Okay, this basis chain that we did actually has a name. It's called the discrete Haar wavelet basis. Okay, people in signal processing use, basically, if you have a piecewise linear function, then it has a sparse representation in terms of this Haar wavelet basis, which is what we are doing.
So the Haar wavelets actually preserve the sparsity.
Up to this log n factor, yeah, exactly.
I see.
Yeah.
Is that the main reason also they do Haar wavelet?
I think so. I mean, that's one reason.
Yeah. Okay.
Okay. So if you put these things together, you get that the noiseless SLR. I'm only saying noiseless because I didn't put the dependence on sigma squared. The theorem actually works even in the noisy setting. You get, basically you'd reduce to the old case, and whatever you had there will apply with k log n sparsity instead of k sparsity. Okay. So you lost some optimality in sample complexity. You went to k log squared n instead of k log n, which again, there's some important reasons why it could be critical, but at least for now, we're shooting for k versus little of n, so a log loss is okay. Okay. You do get a polynomial time algorithm just by preconditioning, right? And this is actually random walk is an example of a case where you can do this, right? If you go back to what we used, we didn't choose the exact form of the equations and so on, right? What we used was this Markov property that once I condition on something, I had this independence front and back, which allowed me to kind of only do log n steps of condition, right? So that's exactly what that's the advantage of doing this way instead of working with Haar wavelet basis directly. So I'm going to now look at sigmas which have this Markovian property, right? For any Gaussian distribution or for any distribution in general, I can talk about the dependency graph because I have a bunch of random variables x1 through xn. I can talk about a graph with respect to which they have this Markov property. There are various ways to define it, but this suffices for us, but so let me say that. So whenever there's no edge in the graph, it is informative. If there's an edge, it doesn't say as much. When there is no edge, it gives you some signal. If there is no edge between the vertices I and j, okay, maybe you want to say they are independent. They're not really independent, but they're independent conditioned on the others. Okay? In fact, you only need to condition on neighbors of one vertex. Okay? So you're basically saying that somehow when two things are not adjacent, they could be correlated, but the correlation only comes through these sort of neighbors that I already have. So if I remove them, then they become independent.
So either of the vertices?
Either of the vertices. In fact, all of these things are equivalent. Conditioning on everything apart from I and j, just on the neighbors. For the setup we have, they're all equivalent. Okay? So if I follow this definition, random walk has a very simple dependency graph. It's just the path, right? If I take any two vertices, right, once I condition on a neighbor, they become independent. That's exactly what we used, right? So this is the abstraction that we're going to work with, that for general covariates, you can always define this notion of dependency graph. And Gaussians have this beautiful property that give me sigma, I can exactly tell you what the sort of minimal dependency graph is, right? Okay. So if I want a dependency graph, I can take the clique because it gives me 0 information, but I want the minimal dependency graph. And for Gaussians, if I look at the inverse of the covariance matrix sigma, then the support of that tells me exactly what the dependency graph is. Okay? It's a very well-known fact in statistics. It's used a lot as well. But it just says that people do parameterize distributions by the dependency graph. This is called the precision matrix.
So this is just like the Gaussian graphical models.
Exactly. Yeah. And these, whenever distributions with constrained dependency graphs are very widely studied, especially in graphical models. Maybe, I don't have random walk style time series data, but I say that, okay, my next step only depends on 10 previous steps. My current step, and with some noise, which only depends on 10 previous things, right? So all of those would fit into this kind of stuff, okay? And so even if I tell you that the general dependency graph, every distribution has a dependency graph, right? So we still want to go beyond worst case with respect to sigma. So we're going to characterize nice sigmas by how complicated this dependency graph is, okay? And to generalize what we did for random walk, it was a path, right? Which is like, there are no cycles in it. A generalization of that is to say that your dependency graph is tree-like. If it is a tree, you can still do this. And more generally, as long as it has small tree width, which is a parameter from graph theory, then you can solve it. That's what we'll say. Okay, there's a way to define tree width, but let me only talk about one implication of what tree width implies. It is that there is a good separator in your graph, right? Meaning, there are some constant times many t vertices such that if I remove them, the graph splits into 2 roughly equal size pieces. Okay?
So do you need tree width, or anytime you have a separator?
Anytime you have a separator.
So like planar graph
exactly.
or something?
Yeah, anything is fine. I mean, but they're all coming from
tree width.
Tree width, yeah. Planar graphs don't always have small separators, though.
Isn't there a planar separator theorem?
But it's omega n.
Ah, I see.
It's root n, basically.
Root n.
Yeah.
Okay.
Right. So, in fact, that we'll come to that in a second. So, as long as balance separator just means that I can pick out t things, so the graph splits into 2 pieces, which are like 1/3, 2/3 ratio. So, why would this be useful? Any guesses?
Condition on it.
Condition on it. You break it into 2 pieces, but every time you're
The same thing.
shrinking by constant size. Right? So that's exactly what you do. So you orthogonalize the variables with respect to the ones in the separator. Then you recurse on the p on the left and right halves, basically, which is what we did for the random walk example.
So your graph, okay, I think finite tree width graphs, you can find this separator in
Right.
polynomial times, and you're fine.
So going back to your question about do you need to know sigma, you basically need to know the dependency graph, or a good approximation of what the dependency graph looks like. Okay? And this is actually related to an old algorithm that people use in linear system solving. It's called this nested dissection technique for solving linear systems. We found out later, it's from the 70s. People were using this as a heuristic to kind of speed up some linear system solvers. Okay? And so the recursion depth is going to be O of log n, and the sparsity only blows up by log n again, like t times log n, because you have t in each of these separators. Okay? All right. So you put things together, again, you get k times t times log squared n, right? And low tree width models are models where you have this small separator show up a lot in linear dynamical systems, in autoregressive models where I don't go all the way back in the past, but like, maybe I have a small window, kind of there they show up. There are these things called structural causal models, which also fall into this category and so on. Okay? We just need the dependency graph, as I said. Okay. So now let me, so that's an upper bound, kind of an interesting class of things we can do better. Now let me now switch gears and talk about lower bounds. What do we know here? Okay. So preconditioning, as we saw, has been powerful, has been helpful for solving these ill-conditioned cases like random walk where existing methods failed, right? But can it actually be true that maybe no matter what distribution you have, there is some preconditioner which will actually get the right complexity? That would be great. Even if I don't know what the preconditioner is, maybe there's no efficient way to find it, but at least if I know sigma, I can imagine them doing some pre-processing, and then I can solve the problem efficiently, right? So, it turns out that that's not enough. In fact, even if I know that the dependency graph is sparse, but tree width really gets to the core of what preconditioning can do. Okay? So if the tree width is t, then I can do it with t k square log n. And we show that if the dependency graph is t, then there is a covariance matrix with that dependency graph where no preconditioning will work. Okay? So in particular, if I take the grid graph, right, the dependency graph looks like the grid, then it has very nice sparsity, but the tree width is root n. It's planar, the separator size is root n. Okay?
Any expander is bad for him, but this is, I guess, even simpler in some sense.
Exactly. So basically, any expander will have high tree width, right? But here we're saying even things which look so nice, you fail, right? And you fail not just for doing this iterative thing, but any preconditioning will fail. Okay, so this requires a lot of work because you want to parameterize over all possible preconditioners. We're saying that as long as the dependency graph has tree width t, there is some covariance you can put on it, so that some numerical numbers you can put on there, so that any preconditioning will require t to the 1/20 samples. So preconditioning is not going to get us better than polynomial speed. I mean, even polynomial would be good, but I believe this should be omega t. Is just how we are doing the analysis. Okay. So in particular, it says that there are covariances sigma where preconditioning is not going to get you beyond n to the omega 1 samples. If you want k log n or poly k times log n, preconditioning is not going to work. So it rules out all of those methods. And this was kind of the first such sort of generic lower bound for random designs. Okay?
So it has nothing to do with Lasso or the method down.
Well, preconditioning is there. What you use next is immaterial, just that preconditioning is not going to work. In fact, the lower bound is very strong. It says that there is a solution which looks optimal, but when there's no signal or something.
I see.
Yeah. Yeah?
By any precondition, you mean any matrix S?
Any matrix S, right? So in fact, it can be randomized too. You cannot even come up with a distribution on preconditioners, which will work. So the deterministic proof is easier. Randomized took a lot more work. Yeah. So let me say 1 or 2 minutes about the proof, but your question?
So here you're not using anything other than the structure, but if I add some term that depends on not just the values of the, take it as a weighted graph instead of.
Yeah, that's a good question. Yeah, that's a good question. So it is plausible. GGMs is one such example, for instance, where you have additional thing not just from the dependency graph but also on the weights, but we don't know how to use it. But at least it cannot be preconditioning. You need to do something. I think the preconditioning is actually the weights are not that bad. So I don't know how to.
There might be some quantity that they're violating because you're constructing a very special weight for every tree.
Yeah, that's true. But I have to think about that. I have a feeling it's reasonably robust. You're not really exploiting the cancellations apart from the range of the values. Maybe, I'm not sure. Yeah.
It seems like this, there might be other methods because this sparse, the grid graph, for example, that you show, it's very sparse. There might be something that can work here.
Right.
It's just.
For the grid graph, the lower bound is basically n to the 1/4. In terms of preconditioning.
If you do preconditioning.
Yeah.
But the graph looks simple enough that it is manageable.
Of course. That's the hope. For grid graph, there should be some way. We don't know.
There can be a question what happens with grid graphs?
We don't know.
Okay.
We don't know how to beat little of n actually. Yeah. So for grid graph, what we do gives you root n times k times log n. That's the best we know. Okay. And the way the lower bound goes is you basically prove a lower bound for a grid. And then for any graph, you can find a grid by using this the graph minor theorem and so on. There's a very complicated gadget that you have to use, but to encode like a hard instance in there to rule out any preconditioning. But all of this goes through. Just to say you find this sort of gadget which can embed like ill-conditioned instances and then rule out when preconditioning can work. Okay? But in summary, there are nice instances where you exploit the graphical structure to go beyond worst case analysis in the sense of sigma. So we can get t times k times log squared n. And on the other hand, preconditioning is not going to be our elixir. It's not going to fix all of the problems that we have for sparse linear regression. Okay? There's a tight trade-off, or reasonably tight trade-off with treewidth. Okay, so let me now talk about this in the remaining 10 minutes, say a few words about more recent work. So once again, I'm trying to find cases where we can actually solve with good statistical efficiency, right? So here's another case which is a failure mode for existing algorithms, like Lasso and basis pursuit and so on. So imagine I have two variables, I have n variables at x1 through xn, but two are highly correlated, just two. So x1 is independent Gaussian, but x2 is basically x1 plus some small epsilon Gaussian. Okay, the correlation between them is like 1 minus epsilon. Okay, but on the other hand, my signal is really trying to identify the gap between the two. Right, W star is very sparse; it's too sparse, and it takes 1 over epsilon times the difference between the two. So it scales up the noise basically. So this is what my kind of, if I think of them as vectors, this is what they will look like. Okay. So here the condition number is really bad. There are two things which are really identical. So condition number is really bad. So the statistical guarantees everything goes out the window. They become vacuous. They depend on epsilon. So nothing to do. In fact, Lasso probably requires omega of n samples here. Okay. So how do you? So what do you do in such scenarios? Okay. So even a single sparse dependency among the covariates can spoil these methods. So they're that brittle. So the other kind of sort of beyond worst case bound that we look at is imagine this is the setup that you have. You started out with a good covariance matrix, but somehow some features, a few of them, became correlated, right? So imagine you're collecting data, but there's some redundancy, right? Maybe you're taking temperature, height, weight, and then you're taking something which depends on them. Right? So I have a lot of eigenvalues, lambda 1 through lambda n. Remember, sigma is an n-dimensional matrix. Most of the eigenvalues are good. They have good condition number, but I have few outliers. Right? I have d eigenvalues which are terrible. Right? That's the condition number is bad, but it's coming because of this d things. Right? Once again, as we just saw, even if d is 1, Lasso and basis pursuit and so on doesn't work. But what if, can I do something here? Is there an algorithm for this that requires little of n samples and runs in polynomial time? Okay. And here, if I knew, this doesn't even fit into the treewidth case because if I look at the dependency graph, that could be arbitrary here. Even with a single correlation, I can introduce all kinds of dependency graphs, right? And in this context, we can actually do it, as you'll see, even if I don't know sigma. Okay? Okay, this is not working.
So Raghu, is the following intuition reasonable? If the eigenvectors which are outliers are sparse, then just dropping the coordinates would work. And if they are dense, then they can't make a difference to sparsity.
Almost. The only thing is you don't know sigma.
Okay, this would have been sensible if sigma.
Exactly, yeah. Almost. You had to do some kind of net argument and so on, but that's kind of the thing. Okay, so at least for small k, as we'll see, k and d, you can do this with a little of n sample complexity, and the algorithm is actually very simple. In fact, you just rescale the coordinates in some nice way, and that will fix Lasso. Usually when I think of rescaling, I'll think of rescaling as, okay, each xi should have variance 1, but that's not what you should do. Like if you go back to this example, you should scale x1, leave x1 as it is, but x2 you should scale to 0 almost. right? So that's the kind of thing that you want to do. And in fact, there's a nice, simple, iterative way to rescale things that will fix Lasso. Okay? And in particular, there is an algorithm that runs in polynomial time, requires W star. The number of samples is k to the 4 log squared n for d a constant. Okay, I think the dependence on d is exponential in d. The number of bad eigenvalues. Okay? And let me talk about another case where it's the same algorithm that works for both of these things, but these are the things that show up in practice. I'm kind of separating them out. So the other case is, once again, you have dependencies in your xi's, but they can be explained away by some, by a single conditioning. Okay? So maybe I have like a lot of features which are dependent on my age, and age is also part of the input.
Aren't age coordinates here?
Think of it as coordinates, yeah. Okay, but they're not known to us. Okay, so the assumption is that the xi's are all correlated to each other, right? But maybe there's some hidden variable which, once I condition on it, everything becomes independent. Okay, it's a little bit like the Markov property, but you don't see the edges; they are hidden, like confounders.
Does it have to be a coordinate, or it can be anything?
They're hidden, so it can be anything. So you can imagine that you're generating this whole thing first, right? Where conditioned on these are independent or very well conditioned, but these are hidden from you, right? This kind of shows up a lot in causal models where you assume that there are a small number of confounders, and what you see is a lot of when you look at what you observe, there are a lot of correlations, but once I condition on something, the correlations go away. Okay. So that's the assumption. There is some edge such that once I condition on them, the random variables become well conditioned. This conditioning is overloaded, but one is probabilistic, one is numerical linear algebra, but we don't know what these edge are. Okay. I mean, the assumption that we don't know edge is important because often finding edge is even harder. So definitely, like you don't know edge, and you can ask, okay, this is again a simple case which is of interest. What can you do here? Okay, and there is an algorithm which is the same algorithm which worked for the old case. Actually, there's a way to nicely rescale the variables so that it will work as long as the number of hidden variables is not too large. Okay, in particular, it runs in polynomial time and recovers the W star with k squared plus h times log n. So the dependence on hidden variables is pretty nice. Okay, so the sample complexity is k squared log n plus h.
So rescaling means just multiplying by a diagonal matrix?
Yes, multiplying by a diagonal matrix. So what's the algorithm? I'm calling it clever because it's not just scaling. Okay. So what do? I'm going to start with the initial diagonal scaling, which is what you do every time you enter something into linear regression. I'll say I'm going to scale so that the variance of each coordinate is 1, just to kind of make the units same, right? But then you refine it. How do you refine it? While I can refine it, meaning if there is an index I which can be explained away as a sparse combination of some other things, I am going to decrease its weight by half. Okay, I'm stating it heuristically, like in words here, but everything can be quantified. Okay, so how do I define explained by? It's kind of whether it is a numerically sparse solution of writing xi as a combination of the others in terms of this L1. If it can be, then decrease its weight. It's somewhat redundant when I look for sparse combinations. That's the point. As you're saying, if it's dense, you don't care about. If it's sparse, you just want to throw them away, which is what this is doing. But instead of doing it in one shot, you keep doing it half every time.
So the step 2 is itself a regression problem.
Step 2 itself is many regression problems. For every one, you have to solve a sparse, just standard Lasso regression problem. It's basically like saying if Lasso fails, you learned something, so I'm going to decrease its weight. Okay, you can put the things quantitatively in here, and then you'll end up with this. So there's one caveat which I guess I should have said is that in this bound, when I say polynomial time, the sample complexity has no dependence on the condition number, but the runtime here has log dependency on the condition number, which is okay. Like, we didn't have like log of n. We're really worried about the case where condition number is like n or something. Yeah.
Just doing this one at a time versus like doing like a higher order, removing multiple points together make a difference because you could make it more.
You could potentially. I think the analysis, we actually do it, whatever you can, do it in one pass and then repeat. Like, for every I, you do this in parallel and then go to the next run. In fact, in our thing, we do something like that because that way you control the number of times each one goes through, like log cap and shows up. Okay, so in the interest of time, let me speed up a little bit. And once again, when you implement this rescale lasso, it's a reasonably simple algorithm. It's just like a few more lines to standard lasso, and it works very well in practice. Okay? And finally, let me say a lower bound. And the lower bound is, so for sparse linear regression, in fact, we did not have anything which was like little omega k lower bound. Okay? Under any plausible assumption before. And we show a lower bound that under this assumption called negative spiked sparse PCA. If you want to know more about it, I can tell you later. But this is some assumption that has been studied in the computational versus statistical gaps literature in several places. We show that under this hypothesis, that this problem is hard to solve, any efficient algorithm will require k squared log n samples. Okay, it's not getting to little of n, but saying that at least you cannot get k log n, which is the information theoretical optimal thing. Okay, and there's an independent work that just showed up like a week ago by people from ETH Zurich.
Yeah. Buhai, Ding, and
Tengel.
Tegel.
Yeah, sorry, yeah.
And Buhai is the same as my co-author on the previous talk.
Right. So they get this lower bound also based on negative spike sparse PCA, the same k squared. And I should say that this is a case where the number of latent variables is constant. It falls into the case where you become well conditioned after you have constant latent variables. So the k squared plus h we saw for the latent variables, that's basically tight unless you believe this negative spike sparse PCA assumption is false. Okay? So I won't tell you much about the assumption, but you can show that it holds under low degree algorithms and so on. Okay, so in summary, we can solve SLR efficiently if covariance has these properties. Maybe the graphical structure is nice, parameterized by some property of the dependency graph. Maybe you have bad correlations, but there are only few of them, parameterized by how many bad eigenvalues do you need to throw away to get good condition number. Maybe most of them can be explained away by just a few latent variables. In all of these cases, we can. And in terms of lower bounds, preconditioning methods are not going to do what we want, even up to like little of n. Low degree algorithms cannot achieve the information theoretical optimal k log n. They can probably best get to k squared, which will be amazing, but we don't know that. Okay? And the obvious problems are, can we do better for sigma? And my favorite question is, we don't have candidate hard instances. Often we don't know how to prove hardness, but here we don't know what would be hard, which I think is very interesting. Okay, thank you for listening.